So in this next lesson of Homework Packet 4.1, we're going to take a look a little more closely at the idea of inputs and outputs, but we're going to do it in the context of what is called domain and range. Domain and range. So what are domain and range? If you haven't heard those words yet, or if it's been a while since you've heard them, they simply mean something that you're already used to. The domain, simply put, is the set of all possible input values for a specific relation. So your domain is nothing more than your inputs. The x's, what are you putting into the relation? And the range is the set of all possible output values for a specific relation. Output. So your domain is your input, that's your x's. Your range is your output, that's your y's. So domain is x, range is y. Now, not every relation uses up all the x's and all the y's. Some relations only use up specific x's and specific y values. For instance, take a look at these tables down here. This relation described in this table doesn't use up all the x's. It just uses up these x's right here, and it uses up these y values right here. It doesn't use up any of the other x's or y's, just those values. So the domain isn't all possible x's that exist. The domain of a function or a relation is simply the x's that you're actually using. And what we're going to do from a table is we're going to state the domain and range in roster form. So here's how we state it in roster form. We simply put domain is equal to, and we have these little curly braces. Okay, it's not a bracket. It's not a bracket. It's not a parenthesis. It's not a square bracket. It is a curly brace. That right there signifies mathematically that we're about to list a set of numbers. So my domain is the set of numbers. Now I'm going to take a look here, and I'm going to list from smallest to greatest. -2, -1, 0, 1, 2, 3. This, and then close it off with another curly brace. This is a statement that says the set of numbers -2, -1, 0, 1, 2, and 3. So that's my domain because that's all the inputs, that's all the x's that my relation uses up. So what then is my range? My range is the set of all of the y values, all of the outputs that I get out of my relation. I need to list them though in order from smallest to greatest. So let's see, I'm going to go -7, -5, -3, -1, 1, and 3. And close it with another curly brace. Now, in this example, we were lucky because everything was listed already from smallest to greatest. However, what if we look at this example over here? What is the domain in roster form? Domain is equal to the set of numbers. Here are my inputs. Here are the x values. Smallest one is -2, and then I've got a 1, 3, 5, 7, 9. So my domain is the set of numbers -2, 1, 3, 5, 7, 9. Those are my inputs. Those are the x's that this relation shows. What then is my range? Simply put, my range is the set of numbers. So you start with the smallest. I'm going to go 2, 3, 4, ooh, how do I treat this? I have 5 twice. I only list it once. So 5, and then I have the 7. These are the y values that I use up. It just so happens that one of the y values is used twice. So that is my range in roster form. Now, unfortunately, relations or functions aren't always presented in these nice tiny little tables that only have 5 or 6 inputs and outputs. More often than not, relations use a whole lot more inputs and outputs. Okay? As illustrated by these graphs right here. Let's take a look at this first one right here. This is a parabola. Okay? That's what you get when you graph a quadratic. Remember that from Algebra 2, or Algebra 1, sorry. And we know that a parabola goes up and out forever and ever if it opens in that direction. If it were to open down, it would go down and out forever and ever. And we know that this comes down to this point right here, which it turns around and then starts going back up. So we've got to ask ourselves a couple things. If my domain is my x's, my inputs, here's the question. Is there any x's that my graph doesn't get over to? Now it goes up, but it also goes out forever and ever. So isn't it always going to be the case that no matter how far I go over on the x-axis, my graph will get over there at some point, and no matter how far over I go on the left to the left, my graph is going to go forever in that direction. Okay? So realistically, is there any x value that this graph doesn't reach to the left or right? And the answer is no. It goes forever in the left and right direction, in the direction of the domain. So here's how we write this. We say that our domain is equal to r, with a little extra line right there. That symbol right there means all real numbers. So in other words, it's saying it's using up all the x's. It goes forever in the left and right direction. What about my range for this one? What about my range? So I look at my graph. I know it goes up forever and ever. However, is there a point at which it stops going down and I don't use up any more y values below it? And yes, there is that point. It comes down here. I believe that's a 2. So it comes down here to a y value of 2 and then goes back up again. So we could state it a different way. Does this graph right here ever get down to 1 or 0 or -1 or -2? No, it never uses up any of those values. It's always greater than or equal to 2. And that right statement right there is exactly how we're going to write the range. Our range is all the y values greater than or equal to 2. The range is all your y values greater than or equal to 2. Because remember, domain is the x's. Realistically, I should have written this one over here. The domain is x equals all real numbers. Okay, and here, my range is not all real numbers because I don't use up any of the values down here. I only use up values greater than or equal to 2. So my range is greater than or equal to 2. What about here? What's my domain? Here I've got a line. This line goes up and out forever and down and out forever. If that's the case, the domain is left and right. That means that my domain is x equals all real numbers because my graph always travels to the right and to the left forever and ever. Okay. Well, what about my range? My range. Okay. If the graph goes up forever and down forever, is there any boundary that I can write or draw that my graph doesn't go above or below it? And no, because it goes up forever and down forever. Therefore, my range is y is equal to all real numbers. Y is equal to all real numbers. Okay. We've got 2 more to look at here. So this one was a quadratic. This right here was just a linear equation. This one right here, we're going to learn to graph them in Unit 5. Right now we're just going to look at them and be able to determine. We're going to look at them already graphed. This right here is the graph of a radical equation. A radical equation always has a starting point, and it either goes up and out forever, or it has a starting point and goes down and out forever. One or the other. In this case, we want to determine domain and range. So let's look at domain first. It looks up like I use up all these x values because my graph goes forever in the x direction over here. However, my graph comes and stops right here. That means -4 isn't being used, -5 isn't being used, -6 isn't being used. There's a bunch of x values over here that aren't being used. In fact, the only x values that are being used are the x values greater than or equal to -3. And that's exactly how we're going to state it. X is greater than or equal to -3. So -3 and to the right. So greater than or equal to -3 is where my graph exists. It does not exist over here at all. What about my range? Range, remember, is the y values. So when we look at range, it looks like my graph doesn't go up and down forever. It goes up forever because it's going up and out forever. But here's that starting point. It never goes below. It never goes below down here at all. It looks like my graph, I think that's a 4, it's always equal to or above 4. So that's how I'm going to write it. Y is greater than or equal to 4, because my graph is always above that value. I'm never going to get a y value less than 4 out of that function. And lastly here, we have what's called an exponential equation. Okay, exponential, we've been solving those. You have to use logarithms to solve them. So an exponential equation, interestingly enough, operates quite interestingly. Every exponential equation has this line right here, this dashed line, called a horizontal asymptote. A horizontal asymptote. And the graph is either always above or always below that horizontal asymptote. Okay? But interestingly, it's never on both sides. So it's a boundary. Okay? You're either always above it or you're always below it. And interestingly enough, you never actually touch that line. So what's our domain? Okay? Now it looks like my graph goes to the left forever, and it goes up and to the right forever. So it uses up all the x values to the right and all the x values to the left, both ways. So my domain for an exponential equation is x equals all real numbers. However, my range is where it's restricted. Because in this case, my graph is always above this line. It doesn't look like the line is at y equals 2. So my range in this case, since my graph is always above that line, my range is always y values greater than 2. Notice I didn't write greater than or equal to 2. I simply wrote greater than 2 because, as I said, this graph never actually touches this line, the horizontal asymptote. It just gets really, really close to it, but never actually gets there. So that's domain and range in the context of graphs using inequalities, the whole greater than and less than symbols, in order to describe all of the inputs and outputs that a graph uses up.